Well, in this lecture, we're going to be talking about some of the most beautiful objects that have intrigued human beings for thousands of years, and that is the Platonic solids, or the regular solids. Notice that, in fact, there is no reason to end. We could have a 7-sided figure, an 8-sided figure, a 9-sided figure, 10-sided, 100-sided figure, million-sided figure. And in fact, one way to think about a circle is that in a way, a circle is an infinity gone. It's what you got if you actually went to infinity and had infinitely many sides that were all equal distance. So in the plane, we have as many regular planar objects as we wish, one for every counting number. Well, having investigated the two-dimensional arena, now let's move to three-dimensional space and think about the most symmetrical object we can think in 3 dimensions, which is the sphere. Well, the sphere is a beautifully symmetrical object. No matter what way we look at it, it looks the same as from any other vantage point. It's beautifully symmetric, but it's actually hard to make a sphere if you're making it out of cardboard or plywood, because it doesn't have any flat sides. So let's go through the same process that we went through before and talk about what would be the most symmetrical objects we could construct where every face of the object is flat and a polygon, just has a finite number of edges. How could we make objects like that? Well, so we'll put the sphere aside, and start thinking about symmetrical objects. This is the most familiar of these objects. This is a cube. We all see cubes all the time. In the room in which we sit is probably somewhat like a cube. So a cube is like a die. It has 6 sides, and each side is a square. And in addition, at every vertex of the cube, you can see that there are the same number of faces coming out. There are 3 sides coming out from every vertex. And if you turn the cube and you look at every single vertex, it looks exactly the same as any other vertex. So it has perfect symmetry for an object that has square sides. This is the cube. But the cube actually is not the simplest of the regular solids. The simplest of the regular solids is a little bit less familiar, perhaps. It's the tetrahedron. So a tetrahedron here has 4 triangular sides. And every side is an equilateral triangle, and 4 of them make this tetrahedron. Now, you might think of the tetrahedron, if you put it down like this, you might think of it as like a pyramid over a triangle. That's a way to conceptualize. You see, a pyramid, like the Pyramid of Giza, actually has a square base. So that's a pyramid. That's not a regular solid. A pyramid is not a regular solid because there are triangular sides that come up, but the base is square. So it's not the case that every face is identical to every other face. Whereas this figure has every face identical to every other face. And every vertex, the points are called vertices, vertex, has exactly 3 faces coming out from it. So these are the first 2 regular solids. The next regular solid is this one. It's called an octahedron. And you can see the Greek roots of these words, octa from 8. It has 8 faces. And each face of an octahedron is, again, a triangle, an equilateral triangle. And this reminds us of these pyramids again, because if you wish to construct an octahedron, the way you would do it is that you would take 2 pyramids. You have a pyramid on the top and a pyramid on the bottom. And you see they fit together right here in the middle. Here's a square in the middle and a pyramid underneath, pyramid on top, and this forms this 8-sided symmetrical figure, the octahedron. Isn't that beautiful? I think these are great just to look at. Okay, then as we move up, the next one that we have has 12 sides. Now this is getting more complicated. It's sort of interesting. Here each face is a pentagon, 5-sided figure. See, each face is a pentagon. Each vertex is incident to 3 different pentagons. So if I look at this from any vantage point of any vertex, it looks identical to any other vantage point. There are 12 sides to this, 12 pentagonal sides that make this beautiful dodecahedron. And you can do 2, dec 10, and you add them in this case. Do and dec to make 12, to remind you there are 12 sides to the dodecahedron. And then we come to this object, and this is an icosahedron. An icosahedron, it has 20 faces that are triangles, 20 triangular faces. Every vertex has 5 triangles that come out from it, you see? And so if I look at each one, from the vantage point of any vertex, I see 5 triangles coming out, and it has this beautiful symmetry, beautiful symmetry. Now, I wonder if I should just go on and do more, maybe we should just talk about these. You see, I mean, maybe there are a lot more of them. Maybe the next one has 30 sides or 50 sides or something. Do you think we should go on? Maybe I should just talk about these for now. Well, actually, I think I should just stick to these, and the reason is that these are all there are. Unlike the case for the plane, where you could have a triangle, you could have a square, you could have a 5-sided figure, 6-sided figure, 7, 8, 9. You could have any number. You had infinitely many different figures, each of which was completely symmetrical. For the 3-dimensional figures, this is all she wrote. This is all there are. There are no more than these 5. And in fact, these 5 were known, there were known to be only 5 of these regular solids back in ancient times. And Plato was so interested in these and thought that it made some special significance to the number of 5 that he associated the elements of the Greek world, one with each of the regular solids. So it has a historical allure that has endured for thousands of years.